Ali, for inviting me, and thank you for the honor of being the first speaker. I hope I can manage this task okay. I probably will prefer not to be interrupted too frequently because the talk is quite tight for 25 minutes. I want to tell a story, but
Sure.
if something really is bothering someone, then please do interrupt me to make sure that that you're following me. So I want to talk about crystals, and crystals form normally from a liquid through a phase transition. And these phase transitions are phase transitions that we call symmetry breaking phase transitions, because what happens during these kinds of transitions is that we start from, in this case, the liquid is a uniform structureless phase. Through the phase transition, as we change some external parameter like a temperature or a pressure, this uniform phase, which has all translational and rotational symmetries, continuous group of symmetry operations, when it goes through the phase transition and the structure evolves, the crystal crystallizes, then one loses some of these symmetry operations. So the basic theme of what I'll be talking about are these kinds of phase transitions through which I will try to explain what these quasicrystals are. These phase transitions where two things happen simultaneously. Order is generated, structure which has long range order in space, while at the same time symmetry is reduced. And when we discuss these kinds of phase transitions, there's a series of questions that one normally asks, and I'd like to go through this sequence of 4 or so questions through which I will hopefully give you some very, very basic flavor of what we're dealing with when we're talking about these crystals that are not periodic, these quasicrystals. So I want to start with the first question, which is, what is the order parameter? So we're going from a structureless uniform phase to an ordered phase, and this has to be somehow indicated by some kind of order that appears, and I would like to have some parameter that will signify the fact that order has appeared. But before I can answer this question, I really need for us all to be on the same page when we're using the word crystal. So what is a crystal? And as you all know, it's a famous story. Before Shechtman's famous discovery in 1982, essentially our understanding was that a crystal is an ordered solid. And if it's ordered, if there is correlation in the positions of the particles that compose this crystal, the atoms or the molecules, then the crystal has to be periodic. And for a periodic crystal, we learned for about a century or more that it has a lot of very nice features. Among those features is the fact that when we perform diffraction, like this image here on the right, then the diffraction, which is actually the Fourier spectra of the material, or the density function of the material, contains pure points, contains Bragg peaks or delta functions, whose positions is closed under vector addition. And in the case of periodic crystals, they form a discrete periodic lattice. And in 3 dimensions, this is so restricted that there are only 14 possible types of such lattices, so-called Bravais classes of lattices. And the symmetry groups, the point groups that these crystals can have, are also very strongly restricted. And we all know that axes of symmetry can only have 2-fold, 3-fold, 4-fold, or 6-fold rotational symmetry. Now, this is not exactly true, because already in the 1960s, through work of de Wolf, Jenner, and Jensen, it became clear that you can actually take a periodic crystal and slightly modify it in such a way that it loses its periodicity, but it still retains its correlation in space, it still retains its long-range order, it still retains its Bragg peak diffraction. So you can do that by taking a periodic crystal and, for example, modulating the positions of the atoms where the wavelength of the modulation is incommensurate with the basic period of the crystal. So what happens is that the diffraction shows additional Bragg peaks, but you do not destroy the Bragg peaks that you had there earlier. So this still remains an ordered crystal, but it's based on the fact that we started for something periodic and then we slightly modified it. And it was really only until Shechtman's discovery in '82 that we realized that the diffraction spectrum of a structure can contain Bragg peaks, even if that structure has nothing to do with periodicity. So the structure is not periodic, but still might contain a diffraction spectrum, might have a diffraction spectrum that contains Bragg peaks. And the positions of these Bragg peaks are still closed under vector addition in this Fourier space or reciprocal space, but their positions are no longer restricted as strongly as they were when the crystal was periodic. And with that, the restriction on the rotational symmetry is also removed. So I want to talk more generally about both of these types of crystals, those that are periodic and those that are not. And in fact, in the early 90s, the official body, the International Union of Crystallography, redefined the notion of crystal. This is not a quote of the new definition, but it's the gist of what it means. Today we say that a crystal is a solid which has long-range order, so there are correlations in space. In space, the positions of the atoms or the molecules are correlated in space, and when that happens, one can have this kind of Bragg peak diffraction. And this is a very typical image for a diffraction spectrum. You can count the number of peaks in each ring here. There are 10 of them, so this is a 10-fold symmetric crystal. If I think of rho of R as being, say, the electronic density of the crystal, then through X-rays, what we can see is an image like this. And the main point is that this Fourier transform is carried by a countable set of wave vectors rather than a continuum or an integral over K space. And what we see here are the magnitude squared of these Fourier coefficients. Usually we can generate these wave vectors by a basis containing a finite number of elements. This is what we call the rank of the crystal. So in this case, I can choose, for example, these 4 points that are labeled with yellow lines, and with them, just by taking vector sums, I can reach all the other points in the crystal. Physicists often call this still the reciprocal lattice. Mathematicians are usually more careful because this is in fact a dense set of points, and more appropriately called a Z module or the Fourier module of the crystal. Now, if I take the rank of the crystal, the number of vectors I need in order to generate it, and compare it to the dimension of the crystal, say the number of components in each of these wave vectors, here the dimension would be 2 and the rank would be 4, then we have the following classification. If the rank is equal to the dimension, then what we obtain is a plain old periodic crystal. If the rank is finite, but not necessarily equal to the dimension, then what we obtain is a quasi-periodic crystal. And if the rank is unbounded, then we have the broadest category of what are called almost periodic crystals. When we say quasi-crystal, we refer to this category of quasi-periodic crystals after we remove from them all the periodic ones. So when R is strictly greater than D, we concatenate the term and we call it a quasi-crystal. So now that we know what we're talking about, I want to define this order parameter. So I want to take the density of the material and just subtract its average value. This will be my order parameter field, and I expect it above the melting temperature, above this critical temperature Tc. I expect rho to be 0 everywhere. I expect the density to be equal to its average at every point. And below the freezing temperature, I expect it to be non-zero with these Bragg peaks appearing in the Fourier, in the diffraction spectrum. Now, along with the order parameter, what we have is physicists, and I know that I'm speaking to a broad audience, we have some kind of an energy cost function. This is called the free energy, which is expressed as a functional of this order parameter field that depends on the relevant external parameters, depending on what I control in my experiment, whether it's temperature or pressure or volume. These are external parameters that I can change as I follow the phase transition. And the point is, and this is taken care of by physics, that I can write these kinds of functionals And their most important property is that they are minimized at equilibrium. So if rho of R is the equilibrium of the structure, this will also be the minimum of this free energy that I'm writing. So this gives us a tool to try to understand what will be the equilibrium phase of the system. So if you've taken some thermodynamics, this is in 2 sentences what we do in thermodynamics. And the point is that the way we express these free energy functionals is that they are always 0 when the order parameter field is 0 everywhere. In the liquid state, so above the melting temperature, F will be positive for every non-zero rho of R. So the minimum of F will be when rho of R is 0 everywhere. But below the critical temperature in the crystal state, F will become negative for non-zero. And so the equilibrium state will no longer be the uniform structureless state, but will rather be a crystalline state with structure that breaks this uniform symmetry all over. So this is very basically what we're doing here. So now that we have the underlying structure of the game that we're going to play, we can ask the next question, which is the most important one, and I will probably spend most of the remaining of the talk speaking about this, and that is to describe on one hand the symmetry that is being broken when we go from the uniform liquid phase to the ordered crystalline phase. And once we break that symmetry, it's clear that if we have a particular minimum state of that free energy, a particular crystal that minimizes that free energy, if I apply some of that symmetry that I have lost, it will not be a symmetry of the crystalline state, but it will rather take me from one possible minimum state of the free energy to an alternative possible minimum free energy, of minimum state of the free energy. And I would like to characterize the space, we call it often the order parameter space, the space of all the degenerate alternative minima of this free energy. And I'm happy I can see Teresa's face here in her video, because this is a question she always asks me about. How can we characterize different minima that are actually equivalent in some sense? Okay, so what we would like to consider is the spontaneous breaking of the symmetry of a liquid to a quasi-periodic crystal, one that is expressed as this Fourier sum that I showed you earlier. And we'll remember that when the rank is equal to the dimension, we will be talking about periodic crystals, and when the rank is greater than the dimension, we'll be talking about quasi-crystals that are aperiodic. So in the same, I want to use the same language for both possibilities, periodic or aperiodic, but in both cases, an ordered structure. Now, if I express that free energy that I mentioned on the previous slide in Fourier space, that is, whenever I see my order parameter field rho of R, I replace it with its Fourier transform, and I express it as an expansion in powers and gradients of this order parameter field, then in Fourier space, and believe me if you don't see it immediately, the free energy will have the following form. It will have sums of all the products of Fourier coefficients at wave vectors, in this case n wave vectors from k1 to with some coefficient, and this coefficient will depend on the exact form of the free energy that we've written down. What is general, and I leave that as an exercise for you if you're interested, is that these coefficients will necessarily vanish unless the wave vectors k1 to kn do not sum to 0. So the only way that a product like this will appear in the free energy expansion is if the wave vectors add up to 0. Okay, a hint is that it has to do with the invariance of the free energy to translations. Okay, now using this, I want to ask the question, what is the relation between different alternative minima of the free energy? Okay, so let's do it step by step. Clearly, if I look at this expression here, I realize the two densities, two different densities, rho and rho prime, or order parameter fields, rho and rho prime, are both minimum free energy states of the same free energy, they can be minimum free energy states only if their Fourier amplitudes satisfies the equality of these products whenever they appear in the free energy. Okay, in a generic situation, I mean, there might be accidents, but I'm ruling out accidents. In a generic situation, since these products appear in the free energy, if I have two different densities, they must agree on all of these products for the free energy to be the same, or for both of them to be a minimum free energy state. So whenever the sum of n vectors adds up to 0, the products of the Fourier coefficients of the two densities must be equal. Now, if I Fourier transform this condition, what I find is that two densities can be both minima of the same free energy if all their autocorrelation functions are the same. So again, if I Fourier transform, inverse Fourier transform back all these Fourier coefficients, then I get this integral at the end, which is nothing else but the autocorrelation or endpoint autocorrelation of the density. So the basic statement said not in a very rigorous way is that two alternative minima of the same free energy have to be similar statistically. They have all the same autocorrelation functions, but they're not the same functions, okay? And in fact, crystallographers, and maybe we have some crystallographers in the audience, crystallographers know that these products of Fourier coefficients at wave vectors that add up to 0 are very important for crystal structure determination. These are the so-called structure invariants. Okay, so let's go on. So I want to talk about two such minimum free energy states sharing the same endpoint autocorrelation function. So I better give it a name, and we say that two such states are indistinguishable if they have all the same endpoint autocorrelation functions. And so we can look at these correlation functions. We can start with the simplest one, the 2-point correlation, the simplest non-trivial one, the 2-point correlation. In crystallography, this is called the Patterson function. And if two densities have identical, if two densities have identical 2-point correlation functions, then they will have identical diffraction diagrams. So the diffraction spectra of the two will be the same, which implies that the Fourier amplitudes differ at most by a phase. Okay, so the magnitude squared is the same. That means that they can only differ by a phase. So the difference between rho of k and rho prime of k is this multiplication by a phase, which for every k will be a different phase. So I've defined a function here, chi of k. And if I look at the 3-point correlation function, then I find that this function, chi of k, which we call a gauge function, is a linear function over the wave vectors in L. So the value of chi at k1 plus k2 is the same as the value of chi at k1 and the value of chi at k2. And in fact, it turns out, again, in generic situations, that if two densities share the same 2-point and 3-point autocorrelation functions, satisfying this kind of, generating this kind of structure with a gauge function, then all higher order autocorrelation functions will be identical as well, if the two densities are quasi-periodic, okay? So let's move on. So we've realized now that all the different minima of the free energy are related by gauge functions, okay? So in fact, the set of all gauge functions can be used to label the different minima and characterize this order parameter space that I'm trying to construct here in front of your eyes, right? I take one minimum state to a different minimum state by performing this gauge transformation and multiplication with these phases, okay? And so each transformation that I perform, or each gauge function, takes a particular minimum state into another minimum state. The set of all gauge functions will take one minimum state to all other minimum states, okay? This is the space that I'm looking at. Now, let's see what the structure is. Because these gauge functions are linear, as I mentioned, once we choose a basis, and I'm talking about finitely generated sets of wave vectors, so once I choose a basis containing R vectors for L, each gauge function is uniquely expressed simply by R real numbers, the value of the gauge function on the basis vectors. So the set of all gauge functions is very simply an r-dimensional vector space, which I call V star, over the real numbers. Now, this is not the end of the story. Okay, I want to skip this. I was going to mention something about phasons. So I skip that. If we'll have time and questions, you can ask me. We should still ask, what is the set of gauge functions that leave the broken symmetry state invariant rather than taking it into another minimum free energy state? Okay, so I have a certain state. I apply a gauge transformation. It might take me to a different minimum. This is what I'm interested in, but it might leave that state invariant. Okay, so those I want to mod out. So if I just look at this expression again, then if I want rho of k to be strictly equal to rho prime of k, then clearly if I take a gauge function which is only has integers defined on the basis vectors, then that will leave my function invariant. So this is what I call L star, the set of integer valued gauge functions. Those will leave that particular broken state invariant. But all the other real valued functions that are not integers, those will take me into other states. I have a picture here just to demonstrate that, but I want to finish the story and I'm running out of time. So what we want to ask is, what are the gauge functions that do take a given minimum free energy state into the other minima? And those are clearly, as I said, the V star, the set of all gauge functions, modulo the set of gauge functions that are integer. Okay, so V star modulo L star. So every degenerate ordered state is parameterized or labeled by a set of R numbers between 0 and 1. So in fact, this order parameter space, which mathematicians often call the Hall, or Uwe will correct me if I'm wrong, is an R-dimensional torus. Okay, so an R-dimensional torus is this space of all the equivalent minimum states of the free energy. And I want to complete the talk or finish the talk with two examples of what we can do now that we have this understanding of the structure of the order parameter space. And the first point is the notion of excitations that cost very, very little energy. Okay, and these are the so-called Goldstone modes. So these are long wavelength deformation of an ordered state. So the perfect state is ordered. Now I want to slightly deform it at a very, very minimal energy cost. And this is the way I'm going to do it. I know that a gauge function, chi of k, transform one ordered state into another at no energy cost at all. So what we're going to do is start from a certain point in space. And as a function of space, as I move along my crystal, I apply a continuously changing gauge transformation. So instead of having a constant gauge transformation, a constant set of R values, R real values, I take this chi and I make it a function of space. So I gradually perform a gauge transformation. And if I do this very, very weakly and gradually, slowly, then this will come at a very small energy cost. This would be an R component deformation field. And this is often described, instead of using these, I'm finishing soon, Vitali. This is often described, instead of using just these R values of the gauge function, is described in terms of a slowly varying translation with what we call a phazon, phazon motion or phazon diffusion or phazon flips. So this is one point. And the last point, or second point, is the introduction of topological defects. So I can continuously deform my crystal at a small energy cost, but I can also consider defects in the structure. The nature of these dislocations or topological defects is that away from a dislocation, if I'm very far away from the dislocation, again, I'm very, very close to the ordered state. I'm only very slightly deformed. So again, I want to do the same trick. I want to take an R component distortion field, but instead of just going along a straight line, I want to pick a point and I want to continuously vary this gauge transformation as I surround this point with a circle. Okay, and in polar coordinates, it basically says that I will have a gauge function that depends on the relative angle to the position where I'm looking at. So for example, if X marks the point of the dislocation, then this will be some value at angle 0, and I continuously deform it to some value at angle pi over 2 and angle pi and 3 pi over 2. And when I come back, I'm back at the same structure, so this has to be the same gauge transformation as the one I started with. And so if I'm think about 20 seconds about what this gauge function can look like, then I realize that after 2 pi, I need to change by no more than an integer, and the value of this integer is what we call a winding number. So this is a very typical topological charge that we can associate with a defect, and this is in fact what we have when we're thinking about crystals. Again, whether periodic or whether not. So for periodic crystals, we talk about the notion of a Burger's vector. This is a set of these integers, the winding numbers in for each direction in space. Now for the quasi-crystal, we have more numbers, but we can still talk about this notion. And this is just a little picture showing you how I can reveal dislocations in a quasi-periodic crystal. It's a little difficult to see them when we look at a quasi-crystal. What we normally do is we take the Fourier transform, we filter out one mode, so this is k and minus k, one cosine mode, and then we Fourier transform back, and we see that, for example, in this crystal, I've hidden 2 dislocations with opposite topological charge, one across from each other. So I've addressed all these questions, and the main point to take out of this talk is this wonderful gauge function that really carries a lot of information and is extremely useful when we want to describe what happens. As you've seen, this language applies both to periodic crystals and to aperiodic crystals, as long as they are quasi-periodic. Thank you very much for your attention.
Thank you, Ron.
2 minutes late.
No problem. So all participants could please clap for Ron.
Thank you.
Thank you very much. Indeed, since we have only 2 minutes left, one quick question from the audience, please. Ron, could you show quickly your slide with order parameter? So it was an interesting connection between the free energy and the functional functional rho of R. So I was trying to check if I have understood it correctly.
This is slide. Oh, you're not seeing my screen now.
Don't worry. Have I understood correctly that if the free energy achieves a minimum if and only if a certain functional order parameter also achieves a minimum?
So the basic idea is that, I think this is the best slide to describe that. Okay, the basic idea is that the free energy, which is, just think about it as an energy, but it's a slight generalization of that depending on what I control in the experiment. This is a function, in this case, because we're talking about a field, rho of R, it's a functional of that field. And thermodynamic, there are various fundamental theorems or axioms of the theory of thermodynamics that ensure that in equilibrium, this free energy will be in its minimum value, okay? The physical picture is that we're talking about systems that relax to equilibrium. As they relax to the equilibrium, the value of this free energy reduces gradually. The relaxation to equilibrium reduces the value of this free energy. When does this relaxation cease to happen? When does it stop? When I'm at the minimum and I can no longer further reduce the free energy. This is the physical picture. And so now, in terms of the implications of that, I have a functional which provides me a tool to figure out what is the equilibrium state of the system. So if I find the minimum of this free energy, then I know the equilibrium state of the system. Now, the interesting question here is that when we go from the liquid phase to the ordered phase, okay, we're taking a phase which has a lot of symmetry, and because the free energy describes that phase as well, the free energy has that symmetry, but the state that minimizes the free energy has lower symmetry than the free energy itself. Okay, the free energy itself, for example, is invariant under any rotation. But when I have a decagonal quasicrystal, I'm only invariant under 36-degree rotations and not any rotation. Okay, so a 6-degree rotation will take me from one variant of the minimum to a different variant of the minimum. And this is what I was trying to characterize. But they will all have the same value of the free energy because that's where I stopped relaxing. I can't relax anymore. I'm stuck at the minimum of this free energy. That's the equilibrium.
Yes, thank you very much, Ron, again. So I'll